Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and welcome back to my channel. For my non-civil engineer viewers joining us, feel free to follow along by treating the technical terms as numbers and applying the process to your own Excel projects. In my last video series, I explained the design of a singly reinforced beam for bending stress, shear stress, and deflection checks in detail using Excel. Now, I'm excited to introduce a new video series, IS-456 Doubly Reinforced Beam Design, Bending Moment, Shear Force and Deflection Limits and Checks in Excel. This is part 1 of the series. If you're new here, I encourage you to check out parts 1 through 7 of my IS-456 Singly Reinforced Beam Design, Bending Moment, Shear Force and Deflection Limits and Checks in Excel series to build a strong foundation. In this episode, we're focusing on the critical aspect of bending stress for a doubly reinforced beam section. Although I'm discussing doubly reinforced beams, this is also applicable to doubly reinforced slabs. In this episode, we are going to cover the following. What is a doubly reinforced beam? Where should we use a doubly reinforced beam? Formulas for bending stress in a doubly reinforced beam. I hope you find this tutorial insightful. Your feedback and questions are always welcome in the comments section below. If you found this video beneficial, please like, share, and subscribe to your community. Let's move to the next slide. Now, the question is, what is a doubly reinforced beam or section? And what are the differences between a singly and a doubly reinforced section? As we progress through this video, the picture will become clear to you. The nature of bending moment is such that it induces maximum stresses at the outermost fibers of the vertical plane. These maximum stresses are compressive in one half and tensile in the other half, with zero stress occurring at the neutral axis. For now, to introduce you to the doubly reinforced section, it's important to understand that in a singly reinforced section, as shown in Figure 01, the bending stress in tension is primarily resisted by the provided tensile steel, AST, and the bending stress in compression is primarily resisted by the concrete. However, in the case of a doubly reinforced section, as shown in Figure 02, we provide steel reinforcement in both the compression zone, ASC, as well as the tension zone, AST, to resist the respective bending stresses. In tables 45 to 56 of SP16, you will find two steel percentages, related to the ultimate moment, mu, divided by BD square, which is related to bending stress. These two percentages of steel are denoted as PT and PC. The full form of PT is percentage of steel in tension, and that of PC is percentage of steel in compression. By reinforcing both the compression and tension zones of the section with steel, the overall dimensions of the section can be reduced. Consequently, we can decrease the depth or width, or both, to fit the structure within a confined space. However, when designing a doubly reinforced section, we must be particularly careful regarding the other two critical factors, shear force and deflection. The limits for these two factors must remain within acceptable boundaries. The symbolic picture of a doubly reinforced section we observe here clearly shows reinforcement denoted by ASC and AST, representing the area of compression steel and tensile steel, respectively, as I mentioned earlier. Let's move to the next slide. Our next question is, where and when should we use a doubly reinforced section? As per SP16, Section 2.3.2 on doubly reinforced sections states, doubly reinforced sections are generally adopted when the dimensions of the beam have been predetermined from other considerations and the design moment exceeds the moment of resistance of a singly reinforced section. The additional moment of resistance needed is obtained by providing compression reinforcement and additional tensile reinforcement. The moment of resistance of a doubly reinforced section is thus the sum of the limiting moment of resistance mu lim of a singly reinforced section and the additional moment of resistance mu lim. Given the values of mu which is greater than mu lim, the value of mu can be calculated. So, in simpler terms, what does this mean for us? Essentially, you use a doubly reinforced section when your beam size is already fixed, but the forces acting on it, the design moment, are too large for a standard singly reinforced beam. To handle that extra load, you add more steel, not just in tension, but also in the compression zone of the beam. For a clearer understanding, let's move to the next slide. Title of this slide is, Explanation regarding a doubly reinforced section. This slide illustrates a common scenario where a doubly reinforced section becomes essential for structural designers. We're looking at two potential designs for a small rail bridge deck spanning a road. Figure 1 shows a design using a singly reinforced beam. Notice the resulting depth of the beam leaves a clear height of only 3.5 meters above the road. If a minimum clearance of 4 meters is mandatory, perhaps due to traffic regulations or other site constraints, this singly reinforced design, indicated by the red X, becomes unsuitable. Figure 2 presents an alternative, a doubly reinforced beam design for the same bridge deck. By incorporating reinforcement in both the tension and compression zones, we achieve the required 4-meter clear height, as indicated by the green checkmark. This simple comparison highlights a key reason for using doubly reinforced sections, to reduce the beam's depth when clearance requirements or other geometric limitations prevent the use of a deeper, singly reinforced beam. Hopefully, these simple figures clearly illustrate the necessity of doubly reinforced sections in situations with restricted depth. Let's proceed to the next slide. This slide illustrates the strain diagram for a doubly reinforced section. On the left, we observe a rectangular section with reinforcement bars. ASC denotes the area of the compression steel, and AST represents the area of the tension steel. The effective depth is indicated by D, and it's important to note that D is equal to the overall depth, capital D, minus the effective cover. We define D dot as the depth of the centroid of the compression reinforcement measured from the extreme compression fiber of the concrete member. As shown, D dot is equal to the clear cover plus half the diameter of the compression reinforcement. Similarly, we see the effective cover for the tension reinforcement, CEFF. The value of CEFF is equal to the clear cover plus half the diameter of the tension reinforcement. Now, a key observation, we are including the D dot distance in our strain diagram, but not the effective cover CEFF directly in the strain profile itself. On the right side, the corresponding strain diagram is displayed. The maximum compressive strain at the outermost fiber of the concrete is 0.0035. The strain at the level of the compression reinforcement, which is located at a distance d. From the topmost compression fiber, is given by the expression 0.0035 multiplied by 1 minus d. Divided by xu max. The strain at the level of the tension reinforcement is 0.87 times Fy divided by Es, plus 0.002. As we've already discussed, xu max represents the maximum depth of the neutral axis from the extreme compression fiber, and the strain at this neutral axis is 0. This diagram effectively helps us visualize the distribution of strain across the depth of a doubly reinforced concrete section under bending. Let's move to the next slide for more detailed explanations and calculations. Now, let's see how we find the strain at d. We know the strain at the very top is 0.0035, and the strain at xu max is 0. So, the rate of change of strain, let's call it x, is equal to 0.0035 minus 0, divided by xu max, which equals 0.0035 divided by xu max. Therefore, the strain at d. Is equal to 0.0035 minus x multiplied by d. Which is 0.0035 minus 0.0035 divided by xu max multiplied by d. This can also be written as strain at d. Equals 0.0035 multiplied by 1 minus d. Divided by xu max. This calculation shows how we get the strain value at the location of the compression steel in the strain diagram. Let's move to the next slide for more detailed explanations and calculations. On this slide, we'll explore some crucial aspects of reinforced concrete design, starting with an important insight into xu max and mu lim. To the left, you can see our strain diagram, which visually represents the strain distribution across the beam section under bending. Now, let's look at the formulas. First, xu max. This represents the maximum or limiting depth of the neutral axis, measured from the top compression fiber of the concrete section. The formula to calculate xu max is, xu max equals 0.0035, divided by the quantity 0.0055 plus 0.87 times Fy divided by Es. The whole expression is then multiplied by d. Here, d represents the effective depth of the section. Next, let's consider mu lim, which is the limiting moment of resistance, or the maximum bending moment that the concrete section can effectively withstand as a singly reinforced beam. The formula for mu lim is mu lim equals 0.36 multiplied by FCK, multiplied by B, multiplied by xu max. This entire quantity is then multiplied by the expression d minus 0.416 times xu max. In these formulas, d is the effective depth of the section. B is the width of the section. Es is the modulus of elasticity of steel, a constant value. Fy is the characteristic strength of the steel reinforcement. FCK is the characteristic compressive strength of the concrete. All these formulas I have explained in my video on singly reinforced section in detail. Notice that the value of mu lim depends on xu max, and xu max in turn depends on es, fy, and d. For elements within the same project, we typically maintain constant material properties, such as fck and fy. If we also need to keep the dimensions d and b constant, then xu max and consequently mu lim will also remain constant. Now, if the calculated factored bending moment, mu, exceeds mu lim, it indicates that a singly reinforced design is insufficient, and as highlighted here, mu is greater than mu lim. In this case, we must proceed to a doubly reinforced design. The first step in designing a doubly reinforced section is to calculate the difference between mu and mu lim. We denote this difference as mu2, where mu2 equals mu minus mu lim. This mu2 value becomes the starting point for our doubly reinforced design calculations. Following this, we have the formulas for calculating the percentage of steel. PT lim represents the limiting percentage of tension steel for a balanced section, and its formula is 100 multiplied by the quantity 0.36 times fck times xu max, all divided by 0.87 times fy times d. This formula also I have explained in my video on singly reinforced section in detail. Then, PTREQ is the required percentage of tension steel for a doubly reinforced section. As shown here, it's calculated as PT lim plus a fraction. The numerator of this fraction is the difference between mu and mu lim. The denominator is 0.87 multiplied by fy, multiplied by b, multiplied by d, multiplied by the quantity d minus 0.416 times xu. Finally, let's look at the maximum percentage of tension and compression steel allowed as per IS-456. For tension steel, PT max is limited to 4%, and similarly, for compression steel, PC max is also limited to 4% of the gross cross-sectional area of the beam. This statement, I going to use in my last episode for the retuning of the design without altering the other parameters. Now, let's move to the next slide for more explanations on how these values are applied. As we discussed on the previous slide, when the calculated factored bending moment, mu, exceeds the limiting moment of resistance, mu lim, we are left with an excess moment. This excess moment requires an additional internal resisting couple. Essentially, the concrete in the compression zone has already reached its maximum capacity to resist the moment mu lim. It cannot provide any further increase in compressive force to balance the additional tensile force required for this excess moment. Therefore, to easily resist this additional compressive force, we introduce steel reinforcement into the compression zone. This is the fundamental reason we design a section as doubly reinforced. On this slide, we have three main figures, along with a simplified strain diagram as a picture-in-picture. For all figures, let's consider the compression zone to be at the top and the tension zone at the bottom. Figure 01 illustrates a singly reinforced section. In such a section, the tensile reinforcement takes the responsibility for the entire tensile force, as concrete is assumed to take no tension. The concrete in the compression zone resists the corresponding compressive force. This configuration allows the section to resist a moment mu which cannot be greater than mu lim. Here, Ft1 represents the total tensile force in the reinforcement, and the section is in equilibrium, shown by its vertical posture. Now, consider figure 02. Here, the applied bending moment mu is greater than mu lim. If only the concrete compression zone and tension reinforcement were present, the internal forces would be out of balance. The diagram is shown tilted to conceptually illustrate this imbalance. To resist this larger mu, a greater total tensile force, Ft2, is required, which is larger than Ft1. This imbalance means the concrete compression zone alone is insufficient. Finally, figure 03 shows the doubly reinforced section. To bring the section back into equilibrium, or its vertical posture, we introduce additional reinforcement into the compression zone. This is symbolized by the spring-like structure at the top of the section. This compression reinforcement provides the necessary additional compressive force to balance the increased tension required for the total moment mu. In essence, the total moment mu is now resisted by two internal couples, one formed by the concrete and a portion of the tension steel, resisting mu lim, and another formed by the compression steel and the remaining portion of the tension steel, resisting the excess moment. The design process then involves calculating the required area for both the compression and tension reinforcement to complete the design. Let's move to the next slide for more detailed explanations and calculations. Now, let's delve into the calculations required for designing a doubly reinforced section. As shown on the slide, we revisit the strain diagram on the left. We start by defining the excess moment that needs to be resisted by the additional reinforcement. As per the formula displayed, mu2 equals mu minus mu limiting. This is the portion of the total moment that the concrete alone cannot resist. This excess moment is resisted by an additional internal couple, primarily formed by the compression steel and extra tension steel. The lever arm for this additional couple is the distance between the compression steel and the main tension steel. Here, we denote this lever arm as d minus d dot. From this, we can formulate mu2 in two ways, based on the forces in the steel. Firstly, mu2 can be expressed as the area of extra tensile reinforcement, which is AST2, multiplied by 0.87 times Fy, and then multiplied by the lever arm d minus d dot. Alternatively, mu2 can also be expressed in terms of the compression reinforcement. This is ASC, the area of compression reinforcement, multiplied by the effective stress in the compression steel, which is FSC minus FCC, and then multiplied by the lever arm d minus d prime. Here, FSC is the stress in the compression reinforcement, and FCC represents the compressive stress in the concrete at the level of the compression steel. To clarify the terms used in these calculations, AST2 refers to the extra tensile reinforcement required for the excess moment. ASC is the area of compression reinforcement. FSC is the stress in the compression reinforcement. FCC is the compressive stress in the concrete at the d dot level, which is the depth of the compression steel. Finally, you see a reminder about the partial factor of safety for steel, denoted as gamma ms. This factor, equal to 1 divided by 1.15, is applied to the characteristic strength of steel, Fy, resulting in the design strength of 0.87 times Fy. This ensures a safe design. Let's move to the next slide for further details on how to apply these formulas. Table F, stress in compression reinforcement FSC, Newton per square millimeter, in doubly reinforced beams with cold worked bars, clause 2.32. Now, let's look at Table F, which details the stress in compression reinforcement, denoted as FSC, in Newton per square millimeter. This table is specifically for doubly reinforced beams utilizing cold worked bars, as outlined in clause 2.3.2 of the relevant design code IS-456. As you can see, for values of d/d up to 0.20, FSC is given as 0.446 times FCK. However, for mild steel reinforcement, FSC would be equivalent to the design yield stress, which is 0.87 times Fy. The table itself provides values for FSC for different ratios of d/d, all up to 0.20, when cold worked bars are used as reinforcement. Below the main title, you'll also notice the formula for the ultimate moment capacity, μ2, which is calculated as AST2 multiplied by the difference between FSC and FCC, and then multiplied by the effective depth d minus d dot. Looking at the table itself, on the left, we have the yield strength of the steel, Phi, in Newton per square millimeter. We have two rows here, one for 415 Newton per square millimeter and another for 500 Newton per square millimeter. Across the top, we have the ratio d/d, with columns for 0.05, 0.10, 0.15, and 0.20. Let's examine the values within the table. For a yield strength of 415 Newton per square millimeter, at d/d equals 0.05, FSC is 355. At d/d equals 0.10, FSC is 353. At d/d equals 0.15, FSC is 342. And at d/d equals 0.20, FSC is 329. Now, for a yield strength of 500 Newton per square millimeter, at d/d equals 0.05, FSC is 424. At d/d equals 0.10, FSC is 412. At d/d equals 0.15, FSC is 395. And at d/d equals 0.20, FSC is 370. This table is crucial for accurately determining the stress in compression reinforcement when designing doubly reinforced beams with cold worked bars. Now, for more detailed explanations regarding these points, let's move to the next slide. Title of this slide is, How to Develop a Table, for FSC at D. Level. In this segment, we'll delve into how to develop a comprehensive table for FSC at D. This slide showcases a detailed approach to calculating and presenting these critical values. On the left side of your screen, you see a table with Fy in Newton per square millimeter across the top, ranging from 250 to 600. Down the left column, we have the d/d ratio, from 0.05 all the way up to 0.20. You'll notice in the initial row, for Fy equals 250 Newton per square millimeter, FSC is given as 0.87 times Fy, which equates to 218 Newton per square millimeter. The bulk of the table provides FSC values for various combinations of d/d and Fy. What's particularly noteworthy here, and something I'd like to highlight, is the inclusion of FSC values for steel grades 550 and 600. By the help of Gemini AI, I have developed the values of FSC for the grade of steel 550 and 600, which are very much available in the market today. These grades are not yet available in our IS-456 standard. If you have any information regarding this, or any special information, please feel free to share it with me. Information is the part of knowledge, and sharing the information enhances our knowledge. Now, let's look at the right side of the slide, which demonstrates the interpolation process. Say, we're aiming to find the FSC value for Fy equals 415 Newton per square millimeter, at d/d equals 0.07. How we can do that? From our table, we know that for Fy equals 415 Newton per square millimeter, at d/d equals 0.05, FSC is 355 Newton per square millimeter. And at d/d equals 0.10, FSC is 353 Newton per square millimeter. The difference in d/d between these 2 points is 0.10 minus 0.05, which equals 0.05. The difference in FSC between these 2 points is 355 minus 353, which equals 0.002. To find the FSC per interval, we calculate the difference in FSC divided by the difference in d/d, which is 355 minus 353, divided by 0.10 minus 0.05. This gives us 40.00. Therefore, finally, to get our desired FSC at d/d equals 0.07, we take 355 and subtract 40 multiplied by the difference between 0.07 and 0.05. This calculation yields an FSC of 354.20 Newton per square millimeter. This detailed interpolation method allows us to find precise FSC values for intermediate d/d ratios. To complete this entire chart, we have to apply this interpolation method for each block of interval, such as 0.10 to 0.15, and 0.15 to 0.20, and so on for all Fy grades. This entire table, which you see before you, you will find in my next video, which will be based on Excel, where I will demonstrate how to easily generate these values. Stay tuned for that. Title of this slide is, Calculation for Percentage of Steel in Compression. Alright, let's now move on to a crucial calculation in doubly reinforced beam design, determining the percentage of steel in compression. This slide outlines the formulas and steps involved in this process. On the left side of the slide, you can see a schematic diagram of a beam section. It illustrates key parameters such as d dot, the distance to the compression steel, d, the effective depth of the beam, and d, the overall depth. You also see the CS representing the compressive force in the steel, and J representing the lever arm. J, is the distance between the centroid of the steel at the tension and compression zone. The diagram further shows the total moment capacity mu lim plus mu2. Now, let's look at the formulas presented in the center. We start with the ultimate moment resisted by the compression steel, mu2, which is given by the formula, mu2 equals to ast2 multiplied by the quantity, fsc minus fcc, multiplied by the quantity, d minus d dot. Here, ast2 is the area of compression steel, fsc is the stress in compression steel, fcc is the stress in concrete at the level of compression steel, d is the effective depth, and d dot is the cover to the compression steel. For singly reinforced sections, we primarily considered the effective depth of the tension steel. But for doubly reinforced sections, we must consider the effective cover for both the compression and tension zones. For the compression zone, this is specifically referred to as the d dot level. While the effective cover in the tension zone is crucial for aspects like durability, fire protection, and proper bonding of the steel, it doesn't directly contribute to the strength gain or diminishing of the concrete section's moment capacity in the same manner that d dot does for the compression steel's contribution. The compressive force, CS, equals to mu2 divided by d minus d dot. As we know, force equals to moment divided by distance, and here distance is lever arm, J. Alternatively, CS can be directly calculated as CS equals to AST2 multiplied by FSC minus FCC. Here, CS stands for the compressive force in the compression steel. From these, we can derive the area of compression steel, AST2. AST2 equals to CS divided by the quantity, FSC minus FCC. Or, expanding on the mu2 relationship, AST2 equals to mu2 divided by the product of FSC minus FCC, and d minus d dot. Remember, AST2 specifically refers to the area of compression steel. Finally, we come to the calculation for the percentage of compression steel, denoted as PC. Here, B is the width of the beam and D is the effective depth. Substituting the expression for AST2 from the mu2 relationship, we get PC equals to 100 multiplied by mu2, divided by B multiplied by D multiplied by FSC minus FCC, multiplied by D minus D dot. And then, substituting mu2 as the difference between the total ultimate moment mu and the limiting moment of the singly reinforced section mu lim, we arrive at the final, comprehensive formula for PC. Therefore, PC equals to 100 multiplied by mu minus mu lim, divided by B multiplied by D multiplied by FSC minus 0.446 multiplied by FCK, multiplied by D minus D dot. In this final formula, we typically use 0.446 FCK for FCC, which is the stress in concrete at the level of compression steel. This systematic approach allows engineers to precisely determine the required amount of compression steel for doubly reinforced concrete beams, ensuring structural integrity and efficiency. And that brings us to the end of Part 01 of each and every step for doubly reinforced beam design, based on IS-456. Today, we laid down all the essential groundwork, and I'm going to be taking a brief break to prepare for Part 02. In the next video, you'll see the practical application of all these formulas right inside an Excel spreadsheet, making it super clear and easy to follow along. Now, for a quick announcement about something many of you have been asking for, the free Excel sheet that I've already demonstrated. I've received so many wonderful emails requesting it, and I'm happy to share it. To get your hands on it, please carefully read the instructions in the description below this video. It's a two-step process. You'll need to send an email with your request and leave a comment on this specific video letting me know you've sent it. Both steps are essential. Once you receive the file, a quick "got it" or "thank you" in the comments would mean a lot to me. However, for this particular beam designing series, since it's truly a do-it-yourself project, I genuinely encourage you to try developing your own Excel sheet first. This is, in fact, my primary objective behind creating these types of videos. The flexibility of pre-made third-hand sheets is often limited, so developing your own will truly empower you. I believe in the power of curiosity. The phrase "I don't know" is often the common starting point for truly wise individuals, those willing to explore and discover something special. It holds great opportunity. We often make the mistake of thinking someone who says "I don't know" is a fool. But let's complete that thought: I don't know, but I want to know. That's where true growth begins. If you encounter any problems at all while developing your sheet, please know that I'm ready to assist you completely free of cost. My goal is to empower you to learn and build your skills. If for any reason you hesitate to take this free assistance, and you feel moved to contribute, you can send some money, whatever your pocket permits, without any burden or pressure. The communication process for that will be the same as for the Excel sheet request. To support me, you'll find the IP address in the description. This communication process helps me understand how engaged you all are and allows me to refine how I share this knowledge with you. I truly hope you enjoyed this episode. Your feedback and questions are always welcome in the comments below. If you found this video helpful, please do give it a big thumbs up, share it with your colleagues and friends who might benefit, and most importantly, don't forget to subscribe for more valuable content like this. Thank you so much for your cooperation and support.